Welcome back, students. So this is actually our first lesson on how our beliefs about the atom have been shaped throughout the course of history. Now, we won't certainly cover every particular change to our beliefs, but just to give you a little bit of appreciation for the idea of the atom being very tiny and our ability to shape our own beliefs about what we believe to be the truth based on a type of evidence called indirect evidence. So kind of a broad theme that will weave a lot of this together is what new thinking did we create as a result of some form of evidence, usually related to the developments in technology. It creates what we would think of as a new understanding. Some people like to call that a paradigm or a shift in paradigm, a change in understanding. So specifically, these are the lesson goals that I thought are a little more specific than the framework that I just spoke about. Okay, so just to make certain that we review a little bit what this idea called a theory is, let's make certain we know what a theory isn't. So a theory is not something that's untested. Something that's untested has been called a hypothesis. So when we talk about theory, there's always some form of evidence, and the evidence suggests that this is a belief that we can support. So, and typically what happens is that technology provides those forms of evidence. Now, what we're going to come to learn is those forms of evidence could either be direct, in which case that's usually pretty solid evidence, or indirect, which is still solid evidence, but shaped by the forms of technology that are available, as our beliefs progress through time. Okay, so that's kind of where we're headed. So this particular slide is about the way that people think. So if we look at this particular set of bars laying on the ground, there's a bit of a debate. Well, how many bars are there? There's 3, there's 4. So they can't agree, 4, 3. And it really depends on how you look at it. And that's really one of the major themes in this segment of our work together this year. We've changed our thoughts about our beliefs about the atoms, about atoms over the course of history, because our beliefs are shaped by the evidence that's available, and technology plays a really, really important role in that evidence that can be available. And more specifically, the type of evidence being what we call indirect evidence. And it sort of has to be that way for atoms because atoms are so tiny, we really can't see them. So we need indirect ways to suggest their existence and indirect ways to suggest their structure or parts or how they're oriented or arranged compared to one another, so on and so forth. So here's another one of those perspective things. Some of you will look at this and you'll see an older woman, looks kind of sad. Some of you will look at this and you'll see a younger woman kind of looking away, looking off back behind us in this direction. So the point is, when we think about our beliefs about atoms, what we believe is based on our perspective, and our perspective can only be shaped by evidence when we're talking about scientific thinking. And we look for evidence from the various, we look to technology from the various times throughout the world, and how that technology has advanced or changed has sort of shaped beliefs. And it may very well continue long into the future. So evidence could come in one of two forms, either indirect, in which case it's not directly seen or witnessed, but we have to develop an inference from it. It allows us to infer what we believe to be a conclusion or conclude from it. A good example of this might be if there were an accident and there were no eyewitnesses and it was a hit and run. So a car drives away and this car ends up in a body shop somewhere. And what they find is they find red paint right on the bumper of the school bus that got hit. So somebody rear ends a school bus and they find front end damage and red paint they find red paint at the scene where the school bus was in the accident, and they find front end damage on the SUV. And that could link together an inference that says, hey, there's a possibility here that this vehicle could very well have been responsible. So this is what we mean by indirect evidence. There's some form of inference necessary to draw that conclusion. If it's direct evidence, then there's direct observation. So we don't need to infer, we witnessed it. So obviously we saw the red SUV drive right into the back of the school bus. Maybe we got the license plate number. Maybe we can even identify what the person looked like, right? So it's kind of like eyewitness type of thing. So even things like fingerprints don't necessarily become what we call direct evidence. In fact, they can, in most cases, be indirect evidence. The fact that at a crime scene, the fact that they find fingerprints of individuals doesn't necessarily prove that they committed a crime, but it proves that they were at, their body was physically at that site somewhere. Unless somebody was able to remove their hand and embed them prints, there's physical evidence that they were present at some point in time. So indirect evidence, right, versus direct evidence, there's a definite difference. Direct evidence, maybe for a crime scene, there was an eyewitness. They saw a person, they had kind of a red shirt on, and they had a black overcoat or covering over top of that jacket. They were a little taller than 6 feet tall. So eyewitness is more like direct evidence, right? Our fingerprint scenario here, kind of like indirect evidence. Okay, so just relate this to atoms.
Good afternoon, everyone. Here are your
We're going to pause. I didn't think you wanted to hear the principal's end of the day announcements, so let's carry forward. Okay. So the theory about the atom, ideas specifically that relate to atoms, it's based upon indirect evidence, which we've settled already. It's been shaped by technology and may continue to be over the years. And what we know is that what people like to do is they like to create visuals to allow people to remember more easily or to show how things are oriented, positioned, compared to one another. And models are nice, useful tools for that. And we often do that even with atoms. So over the course of time, there have been many models. I just want to preview that a little bit with you. And we'll do that right now. So initially, there had to be an idea, a thought, right? So somebody proposes an idea or a thought. They say, hey, there are these things called atoms. Somebody says, yeah, well, prove it, right? And without technology, that isn't really going to happen. So as time progresses, some technology becomes available, and they're able to create some form of evidence that allows people to stand behind, yeah, you must be right. Atoms do exist. So as time progresses, right, atoms get more sophisticated. We start to learn that they have structure, they have charges. And as a result, our view changes. We shift our paradigm, our thinking, and we end up with a new model for the atom. And that new model, which we'll learn about later in the unit, something called plum pudding, but we see the atom starts to go from something very unsophisticated to now, look, it has charges. And soon thereafter, not only does it have charges, the charges are concentrated in the nucleus as positive, right? So the nucleus concentrated positive, but these little tiny electrons, right? So we end up with a new form of model called the nuclear model. And not too long after that, people challenge that model. I say, wow, that doesn't make a lot of sense. This idea of electrons not necessarily being attracted to the nucleus, which we know is oppositely charged. And as a result, there's a concept or a notion of what we call the planetary model. Think about the planetary model. You could think about this, the space shuttle. If this is the Earth right here, so the red sphere in the center is the Earth, and this is the space shuttle in orbit. Well, what we know is that the Earth has what we would call gravity, because it's a very, very large object. And as a result, because the Earth has gravity, what we know is that, excuse me, I didn't mean to make an eraser pen here. I did that accidentally. We know that Earth should attract these things like the space shuttle, and the space shuttle should just come crashing in. Well, what prevents that is the space shuttle has what we call momentum, thrust, right? And as long as the space shuttle, maintains that momentum, it will continue to orbit. if it loses so much momentum that it cannot overcome the pull for gravity, it'll come crash into Earth. So the idea of this planetary model kind of comes from the notion that electrons carry a specific amount of energy, and therefore they don't come crashing into the nucleus. So anyway, over the course of time, that was developed. And what we're going to learn an appreciation for is a little bit about how do we get from here, the idea, to the first model today. And then we'll progress through some of the other significant discoveries as our time together permits in this unit. Okay, so we date this back to really, really early Greek culture. There's a pretty well-respected, what we would call philosopher, probably the most influential philosopher of all time, probably one of the first true educators, had his own school, founded a school. So very well respected by, the community abroad, so to speak. So if he said something, if Aristotle said something, people pretty much got in line and believed him. So he proposes this idea that everything is made of just four components, which we know today as elements: air, fire, water, and earth. Soon thereafter, one called ether, because they were having some trouble explaining phenomena. So they made up this fifth one called ether. So anyway, there are a number of people that stood in line with exactly what Aristotle said, because he's very well respected. And as a result, people they like to, fall behind those people that they know to be really intelligent or their beliefs. So there is another group of folks that we call atomists who have a different belief. And really their belief differs in a very specific way. They sort of believe that there was an infinite quantity of atoms that could possibly exist. So they didn't believe in this idea of there being only 5 elements. They believed that there must be kind of like an infinite quantity of atoms that exist in the world. So some of the people that are given early credit for that, one that's found in a lot of textbooks would be Democritus. There's also a gentleman by the name of Leucippus, but not mentioned in this particular lesson. So this didn't happen in isolation. So other people shared this atomist belief. And atomists said that atoms are tiny indivisible particles, and there's many of them, not 5 like Aristotle said. So it would kind of go from this thinking: if we take a piece of paper and we tear it in half, and we tear 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 in half. Remember, atomos is the word for atom in Greek, which means indivisible, and we tear in half, and we tear in half. Eventually, we get down to pieces that are so small that they're the last 2 pieces that we could no longer subdivide. And that's what the concept of atomos means: indivisible. So Democritus and other atomists believed, that there were sort of an infinite quantity of atoms that might make up everything that exists in the natural world or the physical world. So he's credited for proposing what we call a hypothesis. It's called a hypothesis because people say, yeah, prove it. And with limited technology, it's going to be a very, very difficult idea to prove. So there are kind of 2 camps: the 5 elements camp and the atomist camp. And we went almost 2,000 years before any real hard evidence could be created to get people to accept a new notion or a concept. And a gentleman by the name of John Dalton is the first one, at least in the historical perspective, to come up with something that says, here's some evidence atoms exist. So what he was able to do is take data from experimental data from all these different types of experiments and always come to the same conclusion: atoms exist and combine in whole number ratios when they form new chemicals that we call substances. And I want to show you maybe some way to think about it. We'll come back to this idea with Skittles up here in just a moment. So as a result, he forms a number of statements that we come to accept today as atomic theory, Dalton's atomic theory. So maybe this is a good way to kind of help you grasp this. So when atoms undergo chemical change, they do so what Dalton said was whole number ratios, which means the masses of the atoms that we started with remain constant. Every atom has a unique mass that's specific to the identity of that element and that element only. So for example, if we were to take something like 36 grams of a chemical known as water and chemically react it, do something called electrolysis. Electrolysis means to tear apart with electricity. What we'll find out is that we'll get a gas called oxygen and a gas called hydrogen. So we start out with a liquid and we create two new gases out of it. And they can be separated pretty easily because hydrogen's much lighter than oxygen. So this kind of experimentation was possible. And we don't need a lot of sophisticated equipment. We need things like a balance. So if we just think about the numbers 36, 32, and 4, what do they have in common? Well, seems to me they're all divisible by 4. So we could take them, divide them all by 4. We get 9, 8, and 1. So if we start out with, a certain amount of water, we get an 8-to-1 ratio of oxygen and hydrogen. So let's say that for the sake of argument, we start out with a different amount of water, 18 grams of water instead of 36. Well, what we find out is that these are all divisible by 2, right? It would produce 16 grams of oxygen and 2 grams of hydrogen. So Dalton says, wow, look at that. What we make adds up to the original quantity, 18. Furthermore, if we reduce these, they're all reduced by the number 2, 9, 8, and 1. And he says, that's not a coincidence. The only way that we can think about what this might mean is that when these atoms join in some new way, they retain their original mass. So if this is our H's and this is our O's, right? When the O breaks free from the H, it retains its mass of 16. When the H breaks free of the O, it retains its mass of 1. And it doesn't matter what it joins up with, it's going to keep that original mass. And as they break free, piece by piece, it creates whole number ratios. So Dalton comes up with the notion or the idea that every element has a unique mass. And when elements turn into new chemicals, right, we don't create new atoms. We just rearrange those original atoms in some new way. And as a result, it doesn't really matter what quantity we start with. We reveal, in this case, a 9 to 8 to 1 ratio. This is only one example. So many multiple experiments showed the same kind of mass ratios related to whole numbers. And that kind of gives us the idea, if we go back to the Skittles thing that we were looking at a moment ago, that if we were thinking of orange Skittles having a mass of 3, right, and yellow Skittle having a mass of 2, if we were to join orange Skittle with yellow Skittle, we end up with a total mass of 5. They retain their original mass. Likewise, if we have green Skittle and yellow Skittle joined, we start with a mass of 7. We tear them apart. We get one piece with a mass of 2 and another piece with a mass of 5. We just create 2 individual pieces from what used to be 1. So they retain their original mass. John Dalton credited for the earliest version of atomic theory based on mathematical mass ratios. So that information gives you a little appreciation for, hey, look at Aristotle was actually wrong. Water can't be an element. Water can be broken down into simpler things. If water was an element, we wouldn't be able to create a gas called oxygen and a gas called hydrogen. So 2,000 years later, there's hard evidence to say that Aristotle's wrong. Now, I don't know if this data was used that way. I think there's some suggestion to believe that another chemist by the name of Lavoisier was one to kind of state it that way, but that's not really part of today's lesson. So likewise, what Dalton also says, not only that, we can get elements, the same 2 elements, to combine in different ratios of whole numbers, and we can create a different compound when that happens. So we can create what's called hydrogen peroxide, where the ratio is 2 O's and 2 H's, right? H2O2. Or we can join those same 2 elements in a 2-to-1 ratio, right? H2O. They're made of the same elements, but there are different mass ratios present. So a 2-to-1 ratio versus a 2-to-2 ratio creates a different chemical, even though it's made of the same elements, and the masses of the O's and the H's are still identical no matter what ratio they're combined in. 2-to-1 or 2-to-2, H's have their original mass, O's have their original mass. So Dalton's given credit for our earliest version of what we call atomic theory. Many of the ideas which are still accepted and embraced in today in what we call scientific laws. There were 2 significant flaws as discoveries came down the road, which we've already looked at some of the information that suggests that there were flaws. We haven't looked at the evidence as to why we know those things exist. So that doesn't mean Dalton was an idiot, that there were flaws in his theory. It just means that, at the time, there probably wasn't technology for him to think more deeply about disproving himself. So what we do associate Dalton's thoughts are with kind of the first or earliest version of a model that people like to speak about called the billiard ball model, which basically says that atoms don't really have much structure, but they act like tiny hard spheres and retain their mass. So mass of one compared to the mass of another, if they're different elements, they have different masses. Okay, so for example, right, we join H and O, right, the ratio we join them in, right, doesn't matter what ratio we join them in. If O has a mass of 16, it retains its mass. If H has a mass of 1, it retains its mass. That means the mass of this stuff would be 18 as a result. Okay, so atoms keep their mass as they combine in new ratios. Moving forward, so what are the statements that are more specific to Dalton's original belief? Well, one was that all matter is made of atoms, and atoms we think of as indivisible and tiny hard spheres. Today we know that this to be a flaw. We know that there are protons, neutrons, and electrons that atoms can be further subdivided into. So Dalton wasn't aware of that, lack of technology. As a result, he's not an idiot, just that he's not looking to prove otherwise, at least with the technology that he's using currently. Atoms of one element are identical to each other. Well, we know today that's not the truth. We have what we call isotopes. Atoms of the same element, different numbers of neutrons. What an idiot Dalton must have been. Of course not. There was no technology to prove that there are atoms of the same element, different numbers of neutrons. But he did say that, look, if there's a different element, right, it is different. The atoms of that element are different to some other. Okay. So moving forward, he said that chemical reactions, when they happen, we don't create new atoms. All we do is rearrange them in some new combination. And finally, what we do know is those combinations relate to whole numbers, what you might call a chemical formula. So those whole numbers allow us to think about the mass that we started with remains constant, but how they're joined, the quantity or the ratio they might be joined in, that's what may vary. So the billiard ball model tells us a little bit about the idea that atoms don't have a lot of structure yet. We don't know about protons, neutrons, electrons. We don't know how they're arranged. We just think about them as tiny hard spheres, but each kind has its own unique mass. And that kind of summarizes the idea of Dalton's beliefs. So that wraps up the lesson for today, introducing ourselves to the concept of what we call the changes in the theory about the atom over the course of time. As we look at our next lesson, we'll kind of take little bits of, okay, how did our understanding come to be changed? And technology and what we believe as a result of the evidence from that technology, that's what we'll be taking a look at. So till the next time, folks, remember to respect your chemistry, but don't fear it. I'll talk to you soon. Take care.